So how do we actually test this in the lab? We're going to be in the lab in H255. We have two of these machines. In fact, this is the actual machine. It's not the same machine, but it is the machine. It's the manufacturer. Tinius Olson happens to be the company. It turns out that Tinius Olson is a company right here in Philadelphia. So it's a local company that we purchased these materials from. And this happens to be very similar to the machine that we have. We have two of them inside the H255 laboratory. And if you haven't used it yet, after viewing this video, you will have used it soon when we actually go into the laboratory and use it to measure things. What this machine allows us to do is to measure all of those things, measure compression and tension and shear and flexure and torsion, all of those different measurements, and do so with one single machine. It takes a lot of accessories, but there's lots of tests we can use. So even though this sounds kind of a haughty name, a universal testing machine, it can measure the universe of every possible situation. Obviously not the case, but it is called a UTM, universal, in as much as the majority of the mechanical testing that we wish to do on any part, compression, tension, shear, flexure, torsion, can be performed by this one single machine with all kinds of adapters on it. So that's why we call it a UTM, or a universal testing machine, and we'll be introduced to it inside lab. What we need to do, of course, is to measure stress and strain. We need to measure the force, we need to measure the area, and then we need to measure distance. How long did it get? So this happens to be a force sensor. That's what it looks like mechanically, and I'll definitely be pointing it out to you inside the lab. The force sensor is attached to the machine, so it measures how strong is the force. It measures in newtons, or it measures in pounds, and converts between the two. And then the other thing we need to measure is distance, and that's how long or short these things are. And what this large tower over here, let me go back to the picture. Here's the force sensor that we just saw. It's mounted right here. That measures how strong or how much force there is with the push or the pull. And then this force sensor is attached to this, what's called a lead screw. It's really a large screw, very, very, very strong, made out of metal alloy, which we'll be talking about later on in the course, that is in this tower. And all what happens is this tower spins this screw and sort of unscrews or screws down this little attachment, and as this thing turns, this thing lifts or this thing sinks, or it rises or it falls. So we can actually calculate how far it has risen or fell based on how long we've turned the screw, and then we can measure how strong this force is. It's a pretty ingenious and very simple machine. But so there's the force sensor, there's the lead screw that's inside that tower. We don't see it. We don't typically take apart the tower to take a look at, but that's what it looks like. But inside there is what's called a rotary encoder. And what a rotary encoder does, there's a machine that goes ahead and forces the screw. It takes a lot of force to turn the screw. But then on the bottom of it is an encoder, and the encoder does exactly as it sounds. It tells us through a calculation how far this screw has turned the force sensor. So it encodes the length into rotation. So the force sensor, the screw, and a rotary encoder, and a computer to control it, and you have a universal testing machine. Pretty cool. So how do we go about compressing these things? In this case, there's two guys right here. This is the platform. This is the platform. This is not actually the one that we're going to use. This is a UTM with two screws. These guys right here, these very hard, flat surfaces that are used to compress things, they're called platens. I guess they could have been called plates, but they're called platens. So that we're going to be using the word platens, and they're called compression platens. I'll be showing you the compression platens that belong to our UTM. In addition to pulling things apart, we're simply going to latch on to the material and pull it apart. They're called grips, very much like you take your hand and grip things. These are very, very delicate wedge grips. You can, if you take a look at these closely, what's happening is this little tiny material is sort of pinched between these two wedges, and as this material is pulled apart, these wedges tend to be pulled down into this grip, and what happens is the result is these wedges get tighter and tighter and tighter. So the stronger you try to pull, the more tight your grip. and we have wedge grips, and we'll be taking a look at those inside the lab. Usually these wedge grips are used for material that is kind of strong, using the word strong, because as these grips get really tight, you don't want them to bite like a pair of teeth. You don't want to cut your material, you want to pull on it. If your material is kind of weak, like a piece of string, then we have what's known over here as bollard grips. These are double bollard grips. A bollard is this little round thing right here that you wrap rope around. So if you notice this guy, I'll follow the rope down here. Here comes the rope. It comes down here. It sort of wraps around this bollard, comes up and then down and around and then gets pinched. What it does, pardon me, what it does is it allows this rope or this cord to sort of gently tighten around this grip without actually cutting it or chomping on it with these grips. We don't want to cut the rope. The word bollard is a word that is not manufactured or made up by the mechanical engineers. A bollard has been around for a while. It's actually a seafaring term. If you happen to own a boat or work on a boat and you want to take a line off of the boat and wrap it around that post that happens to be attached to the dock, it's called a bollard. If you happen to go on a lot of the rails to trails bike paths here in Philadelphia or maybe locally at home, they use a lot of bollards to keep cars off the bike path. And if you go shopping, I think Target's bollards are red, but if you go to a shopping mall and you want to stop customers from accidentally or drunkenly driving their car into the glass front door of your store, then you put up bollard, and these bollards stop folks from driving their automobiles through the surface of the floor, while the surface of the store, while they allow customers and shopping carts to come out. So again, just looking for more vocabulary words. If you want to win a bar bet, you know what this thing is called now. It's called a bollard, and the bollard grips that we're going to use inside our laboratory are called double bollard grips because they have two bollards. That's what a bollard is. Off we go. If we're talking about shear flexure, again, we saw shear was one up, one down force. This guy happens to be a double shear flexure. It's almost like a flexure fixture, if I can say these things without tripping on my tongue. This is a shear fixture. You'll notice this metal pin here, or this metal bolt, is going to be sheared by this central guy here. This thing is going to fit on top, and then we're going to use the UTM to compress these two fixtures together until this pin or this bolt is sheared or cut. We're going to measure how much force it requires to do that. Here's that flexure fixture I was talking about. We have one of these. It sort of looks like this. We go ahead and adjust the span of these individual bases, and then we attach to the center platen, if you will, to our force sensor, put it on the machine, and the machine follows its programming and then brings this thing down while measuring how much force, and then we can measure how much this flex is. So it's just a bending thing. You can think of all kinds of things that might be bent, including the airplane wing we saw. Not so much the iPhone, but maybe a bridge. How far will this thing bend as we put it across the ravine? We would definitely want to do a flexure test for a bridge. Some of these things get pretty obvious. This is a comb fixture. We literally have a plastic comb, maybe a goodie comb that you buy at CVS. We put it in this machine here, and then we have a wig, or we have some sort of material here that's going to act like hair. We're going to tangle the hair, and we're literally going to measure how much force it requires to move this comb through this knotted piece of hair or strand of hair. Obviously, we don't want it to be a lot of force. You'll start pulling people's hair out. So this literally needs to be tested, and this is how they're testing it. This guy happens to be a needle sharpness fixture. So down here, again, all these things have in common a base and a top. This base seems to be holding a material, whether the material happens to be leather or a cotton material like a shirt. We're going to go ahead and put different needles inside this upper flexure fixture. you can go ahead and spin it through, and they can measure the force it requires for the needle to go ahead and puncture the material. If you can imagine, it's not much force if you're sewing up a cotton shirt, but it may be a lot of force if you're stitching, say, a football for the NFL. You have to go through the leather pigskin. You want to measure how strong that force is, and you want to measure how sharp these needles are and how much force is required. So there's hundreds of things we could test. These are just things I grabbed off the internet. Here's happened to be a carpet testing machine. You want to see if your carpet is going to withstand certain things. This guy happens to be a little remnant of carpet. This guy, I believe, happens to have a hollow shell on the bottom, and it's going to push through this upper platen and wants to see how quickly this is going to tear. Usually we don't put carpet, we don't lay carpet over anything but a flat solid surface, but in this case, if it happens to go over a hole in the floor, you want to see how quickly you're going to step through the carpet. We can go ahead and test that. This guy happens to be the most advanced one I have as an example. They literally have a little piece of tissue, I mean human skin. They've gone ahead and they've attached it by these tiny little cords. Each of these cords is attached to these little fixtures, and then they're going to go ahead and pull these things out. It's sort of like being drawn and quartered. They want to see how flexible this soft tissue is. Maybe this is real tissue, so they can get a measure of how quickly this stretches. You'll notice the reason how they're measuring this strain is they've put 4 dots here, and they have a digital camera, and they're measuring how quickly these 4 dots expand as it stretches out. This may actually be a real piece of tissue. Maybe they want to see how soft skin is after you use a hand lotion, or after you use a cleaning material. We want to see how aged the skin is. Or this could be a new skin material, some synthetic skin that somebody has developed, and they want to prove in the laboratory that this soft skin or this soft leather is just as soft as real leather or real skin, which is a way to test it. So any way you can test something, we can finally put a rig together in the lab. Of course, the total goal is going to be, can you mimic the actual situation that your product is going to experience in the customer situation? You want to see and predict how that's going to behave inside the lab. So with that, we're back to the title slide for this guy. So this has been a presentation on mechanical testing. Again, working in the lab, we're going to be working with the universal testing machine. We're going to be take a look at samples and see how we flex things and see how we test things, and then give you guys some experience about how we can dream up putting together different tests for different materials. As we progress through the course, we are going to be receiving our 3D printers. We're going to be putting them together. We're going to be 3D printing our own materials, and then we have the UTM machines to go ahead and test the strength of materials in all kinds of situations, flexure and compression and tension and twisting and whatever you want to do to torture the things that you design. Well, again, we're not torturing them just to see how well they react. We're torturing them to see if you can, one, figure out what design might be the best design structurally to make your product. And then if it turns out that you can make the same product with a little bit less material, in the case of saving plastic or saving metal or saving glass, you can make the material lighter, you can make the material less expensive, and of course that's mechanical advantage for people to use your material rather than something else or your product. So with that, we're going to finish this, and we'll see you on the other side. And thanks again. See ya.